Hi, and welcome to the video. And today we're going to be solving for the hydrogen atom. And this part, we're only going to be writing down the Hamiltonian for our hydrogen atom. So when we've done particle in a box, there's only one particle involved, right? But in a hydrogen atom, we now have our proton and an electron. This complicates things. But the good thing is that the hydrogen atom can be solved exactly mathematically using the Schrodinger equation. In fact, it's one of the very few systems that can be solved exactly. So how do we get started with this multi-particle system? So let's start out by first writing our time-independent Schrodinger equation. H psi equals E psi, right? And our H operator here is the Hamiltonian of the entire system. The wave function is also for the entire system. Wave function representing state of the entire system. And E is our total energy. So let's first define our coordinates for the electron. We're going to have XE, YE, and ZE. And for our proton, similarly, we have XP, YP, and ZP. So our wave function is going to be a function of all of these 6 coordinates, XE, YE, ZE, and XP, YP, and ZP, because this wave function represents the state of the entire system. Now, you must be wondering, why don't we just have psi E for the electron and psi P for the proton? It's because if you have 2 separate wave functions for the electron and proton, it misses the fact that the electron is always near the proton because of electrostatic attraction. So having 2 independent wave functions does not take into the consideration that if you found one particle, the other one is going to be near it. So we have to have a total wave function that describes particles for the entire system. Okay, so let's now write down the Hamiltonian for our hydrogen atom. And now we're going to have 2 kinetic energy components, one for the electron and one for the proton. So we're going to have h bar squared by 2 me delta E and P delta P. And we're going to have a potential energy component, which is going to be a function of the distance between the electron and the proton. And this potential is nothing but our Coulomb potential energy. From electrostatic attraction, and we know that this takes the form of K Q1 Q2 over R, right? So our potential then becomes 1 by 4 pi epsilon naught, which is K. Q1 for electron is minus E, for proton is plus E upon R, which is the distance between the electron and the proton. So this is our potential, Coulomb potential energy. So now to write it more explicitly, our Schrodinger equation, or the time-independent Schrodinger equation, becomes minus h bar squared by 2me delta E 2mp delta V plus our potential energy term times our wave function psi, which we've seen now is a function of xe, ye, ze, xp, yp, zp. This is equal to the energy of our system times, again, the wave function. Okay, so we have our Schrodinger equation now, but our psi is a function of 6 coordinates. So instead of solving this massive 6-dimensional equation, we want to find a way to break down this problem to, say, 2 equations, each of which is a function of 3 variables. And in order to do that, we're going to have to use some clever change of variables. And one of them is to use relative positions. So we're going to define that as x is going to be xe minus xp. Let's say y is ye minus yp. And z is ze minus zp. So you've defined these 3 relative coordinates first. And now we have 3 coordinates, but we know our wave function is a function of 6 coordinates. So we need 3 more coordinates. Where do we get that from? And for that, we're going to use something known as the center of mass. The center of mass is given by this equation. So you multiply the mass of electron by its coordinate plus mass of proton by its coordinate divided by the total mass. So if you wanted to write it more explicitly in terms of x, y, and z, we would have x is equal to me xp. Similarly for y and z. And this is our this is our second set of coordinates. Oh, sorry, my headphone keeps getting unplugged. All right. Sorry. So now we have 6 coordinates again, but instead of the wave function being a function of xe, ye, ze, xp, yp, zp, we're saying it's now a function of xyz, small xyz, and capital xyz. And why we're doing this is going to become clear shortly. The reason is that we don't want to solve a 6-dimensional equation. So we want to be able to separate this gigantic equation in terms of 2 easy to follow equations, 2 equations of 3 variables each. One of them will depend on small xyz's, the other one will depend on capital xyz. And that is precisely why we're defining these new set of variables. So in order to write this monster equation in terms of our new variables, we're going to have to express our del 2E and del 2P in terms of our new variables. So let's see how to do that. So we know del 2E. For example, I'm just doing it for the electron now, and it'll be exactly the same for the proton. And this is given by del 2 by del x2. These are nothing but partial derivatives, right? So let's just assume one dimension for now and just solve for del 2 by del x2. So what we want, let me highlight it, so it's clear, what we want is del 2 by del x2. Oh, sorry, let me be more clear. So this has E subscript, right? Because we had E over here in the del. So we want to write del 2 by del xe2 in terms of small x and capital X. How do we do that? So we're going to do this. So first, let's try to find what del by del xe is going to be. And we can take a derivative of this again to find out del 2 by del xe2. And we're going to use the standard separation procedure that we've seen in calculus. If we want to write it in terms of capital, yes, right? I hope this is clear. This is just a standard variable change that's used in calculus. And now, let's first try to solve this part. We can go back to our x here. And if we take our partial derivative with respect to xe, here it is implicit that this is being solved when xp is constant. We get me upon me plus mp, del by del x. And when you differentiate small x over here, with respect to xe, you get just 1 times del by del x. And we're just going to call me plus mp, which is the total mass of our system, a capital M, right? This is mass of electron plus proton, so this is just the mass of our hydrogen atom. So we have del by del xe is equal to mass of electron by total mass times del by del capital X plus del by del small x. But as you know, we need del 2 by del xe2, so we're going to have to take the derivative of this again. So this part is something we just solved right here. We can substitute that and we get me by m. Okay. This part is again the same thing that we had here, which we've already solved for. So let's substitute that in real quick. Again, the same thing. And this is what we will get. We get me by m, the whole square, del by del x, plus, I'm now writing this term here, del 2 by del x2. And now write down the remaining terms. Okay. So this is our expression for del 2 by del xe2. And just to remind you, why are we doing this? We are doing this because we're going to eventually, we want to find a replacement for this thing, because we don't want to express our Hamiltonian in terms of xe, ye, ze, xp, yp, zp, we want to express it now in terms of small xyz and capital xyz. So we're trying to find a form of del 2 by del xc2 in terms of small x and capital X. So this may look a little bit cumbersome, but trust me, it'll get simpler as we continue. And we can do the exact same thing for the proton, and I'll leave that up to you, but you'll see that we get, sorry, this here is not really the proton mass. And P by capital N. And you'll see when you do the derivative that here you'll have a minus sign, and this minus sign comes from here, because now your xp is negative, you had plus xe, and you have minus xp. So this leads to a negative sign here, which when you try to do it yourself, you'll see how that happens. So this is what we have for our proton. Cool. So let's remember again what we're trying to substitute. We're trying to substitute the Schrodinger equation in terms of xe and xp to small x and capital X, right? So let me just write down this part again. We have our Hamiltonian minus h bar squared by 2me delta e. Plus some potential term, right? So we've seen that our del 2e is something we've already learned how to substitute in terms of x and small x and capital X, and similarly for del 2p. So let's try and simplify it a bit further. We have minus h bar squared by 2 del 2e plus 1 by mq del 2p. And we also have a b term that I'm not focusing on too much right now. Yeah, let's just talk about this part for a moment. So when you divide, so what we're now doing is dividing this by 1 by me, right? Then this by 1 by mp, and adding these two equations together. So we're going to have mp by capital squared by del x plus 1 by m plus, because we're adding these two terms together here, we're going to have mp by m squared minus m here. So you'll notice immediately that this term and this term cancel because of the minus sign. What are we left with? We have me by m squared plus mp by m squared Sorry, just trying to determine if I missed a term. I just cross-checking real quick. Yeah, looks like everything's all right so far. Okay. So we take del by del is common. And the sorry. Yeah. When I divided by 1 by me here, this should have been 1 by m. Right. And this should be 1 by mp. Okay, that's what I was wondering. So del 2 by del x2. Also, this should be okay, perfect. So here you have 1 by me plus 1 by mp. Right. This becomes, so we know that capital M is nothing but me plus mb. Just let me write that down explicitly. So this cuts, one of this goes. What we're left with is del 2 by del x2, 1 by m, plus del 2 by del x2. And this I'm going to call 1 by mu. So you just defined, just so I can write it in a smaller way, we've just defined 1 by me plus 1 by mp to save some space as 1 by mu. And this mu is called the reduced mass. So nothing fancy here. We just wanted to make this a little bit more compact. And so we defined another variable called the reduced mass. So what happens to our Schrodinger equation now? Let's go back here to divide it, multiply it with minus h bar squared by 2. So our Hamiltonian finally is minus h bar squared by 2 del 2 by del x2. Again, minus h bar squared by 2. And then mu plus our favorite potential energy term. Just rearranging it a little nicely, we get 2m and if you want to generalize it for all directions, x, y, and z, for all dimensions, we'll just write sorry, we'll just call this one capital R. We're going to call this small r. So capital R is nothing but x I cap plus y j cap plus z k cap. And small r is small cap is small z k cap. So this, finally, is our transformed Hamiltonian for the hydrogen atom. So what we've done successfully now is, instead of having the energy terms as we saw here in terms of E and P, that is the positions of the electron and proton, we now have our Hamiltonian in terms of capital R and small r, where small r tells us the relative position and capital R gives us the center of mass coordinates. And this is going to be helpful in the next video to separate our wave function. So thanks for watching and hope this was helpful.